Welcome to the deep dive. If you're just starting out in computer science, maybe dipping your toes into AI, well, you're definitely in the right spot today.
Yeah, absolutely.
We're going to unpack something really fundamental: intelligent agents. Think of it as ground zero for understanding how AI actually ticks.
Exactly. We'll be breaking down what these agents are, how they, sense and interact with their world, and the basic ways they tackle problems.
And we're drawing from university lecture notes for this raid.
Hmm.
Stuff designed specifically for students encountering these ideas for the first time.
That's the plan. Good foundational material.
So our mission today is pretty straightforward. Make
Uh-huh.
intelligent agents clear, cut through any initial confusion. We want to build a solid base for you before you dive into more complex AI topics later on.
Sounds good. Let's do it.
Okay, so first things first. What is an agent in this AI context?
Well, at its core, an agent is just anything that perceives its environment using sensors and then acts on that environment using actuators.
Perceives and acts. So like us, our eyes, ears, those are sensors. And hands, legs, actuators.
Precisely. That's a perfect human example.
Yeah.
But it's broader than that. Think about a robot.
Okay.
It might have cameras, maybe infrared sensors, right? And it acts using motors to move around or grab things.
Gotcha. And software too.
Definitely. A software agent could perceive things like your keystrokes or maybe the contents of a file, and then act by displaying something on the screen or, say, filtering your email.
Okay, so it's this constant loop. Perceive, think, act. Is that the idea?
That's the fundamental cycle, yeah. Perceive, think, act.
Now, how does it decide what action to take based on everything it's sensing?
Right, that's where the agent function comes in. You have to imagine a complete history of everything the agent has ever perceived. We call that the percept sequence.
The whole history, not just the latest input.
Exactly. Each little bit of sensory input is a percept. The sequence is the whole list. The agent function is basically the rule book or the mapping that takes this entire history and decides on an action.
Interesting. So it has memory, in a sense.
In a way, yes. The function maps the sequence to an action. And the agent itself, well, you can think of it as two parts. There's the architecture, the physical hardware like the robot body or the computer it runs on. And then there's the agent program. That's the software, the actual implementation of that agent function. So you can say agent equals architecture plus program.
Agent architecture plus program. Okay, I think I'm following. Could we use a simple example? The notes mentioned a vacuum cleaner world.
Ah, yes. The vacuum world. It's a classic for teaching this stuff. Super simple. Imagine just two locations, A and B.
Okay, 2 rooms.
Right. And each room can be either clean or dirty. That's it. Now, the vacuum agent's perception is limited. It only knows its current location, A or B, and whether that location is clean or dirty.
So a percept might be like A, dirty, or B, clean.
Exactly. Just those two pieces of information. And over time, it gets a sequence of these. A, dirty, then maybe it does something, then A, clean, then maybe B, dirty.
And what can it do? What are its actions?
Also very simple. It can move left, move right, suck up dirt, but only if it's in a dirty square, obviously, or do nothing, which we just call noop.
Left, right, suck, noop. Got it. Simple world, simple actions. So how do we know if this vacuum is doing a good job? How do we judge it?
Good question. That brings us to the idea of rationality. A rational agent is basically one that tries to do the right thing.
The right thing. Okay, but what does that mean for a vacuum?
We need a way to measure success objectively.
Right.
That's called a performance measure. For the vacuum, a sensible measure would be, say, the amount of dirt cleaned up over a certain time.
Right. Maybe we give it points, like +1 for every clean square per minute.
Exactly. That would work. A vacuum cleaner that just, I don't know, bumps between A and B randomly isn't very rational according to that measure.
Makes sense. So rationality isn't just about the immediate moment.
No, definitely not. Being rational at any point depends on, well, 4 things. First, that performance measure we just talked about. Second, whatever prior knowledge the agent has about the environment. Like our vacuum might know there were only 2 rooms. Third, the actions it can actually perform. Left, right, suck, noop.
Right.
And fourth, crucially, the entire percept sequence it has received up to that point. Its history matters.
Okay. Performance measure, prior knowledge, possible actions, and percept history. So what's the formal definition of a rational agent then?
Formally, a rational agent is one that, for any possible percept sequence, selects an action that is expected to maximize its performance measure, given the evidence provided by that percept sequence and whatever built-in knowledge it has.
Expected to maximize. So it's doing the best it can with what it knows.
Precisely. It's not about being perfect. It's about making the best bet based on available information.
Okay. The notes had a self-driving car example for this, right? Approaching a yellow light.
Yeah, that's a great one. Think about a self-driving car. Its performance measure involves things like safety, staying legal, maybe efficiency. So it approaches a yellow light. Its sensors tell its speed, distance to the intersection, maybe if there's a car behind it, or pedestrians.
Right.
If it calculates that it's too close to stop safely before the line, the rational action maximizing safety and legality is probably to proceed through the yellow light.
Even though it's yellow. Okay.
But if it has plenty of distance, the rational action is to brake smoothly and stop. Or if it suddenly detects a pedestrian stepping out.
Brake immediately.
Exactly. Safety overrides. It's constantly making these judgments to maximize its performance measure based on its perceptions and knowledge.
That really clarifies rationality. It's practical decision-making.
Yeah.
Now, the notes also mention omniscience, learning, and autonomy. How do they fit in?
It's really important to distinguish rationality from omniscience. Rationality is doing the best with available information. Omniscience means knowing everything, including the future outcomes of actions, which is impossible for any real agent.
Right. No crystal balls.
Exactly. Learning is about the agent improving its performance over time. It uses its experiences, its percepts, to get better at making rational decisions.
So it adapts.
Yes. And that leads to autonomy. An autonomous agent is one whose behavior is determined more by its own learned experience rather than just its initial programming. It learns and adapts on its own.
Okay, so the best agents are rational, they learn, and they become autonomous. Makes sense. How do these agents actually, solve problems then? The notes move into problem-solving agents and search.
Right. So up to now, we've talked about agents reacting or making decisions based on history. But often, agents have specific goals, like get the vacuum to clean both rooms, or get the self-driving car to navigate from A to B.
Goal-based agents.
Exactly. Sometimes called problem-solving agents or planning agents. These agents need to figure out a sequence of actions to reach a desired state, a goal. They have to think ahead, consider the consequences of their actions.
So they're not just reacting, they're planning a path.
Precisely. The task becomes finding that sequence of actions. And the process of finding it is what we formalize as search, searching through the possibilities.
Like searching for the right path through a maze.
That's a perfect analogy. And to do that search effectively, we need to structure the problem properly. That's problem formulation.
Okay, what does that involve?
There are a few key pieces. First, the initial state. Where does the agent start?
The entrance of the maze.
Right. Then, the set of all possible states the agent could ever be in. That's the state space.
All the locations inside the maze.
Then, the actions available in any given state.
Yeah.
So, from a particular spot in the maze, maybe you can go forward, left, or right.
Yeah.
That's the action space. We often write actions to mean the set of actions possible in state space.
Okay. Initial state, state space, actions. What else?
We need a transition model. This tells us what happens when we take an action. If I'm in state since and I take action, what's the resulting state? We often write this as results.
So if I'm at coordinates 3, 4, and I move back, right, the transition model tells me I end up at 4, 4.
Exactly. Then we need a goal test. How do we know if we've reached the goal state? Is this state the exit of the maze?
Simple enough.
And finally, a path cost. This assigns a cost to a sequence of actions. Often it's just the number of steps, but it could be time or fuel used, whatever relates to the performance measure.
Initial state, states, actions, transition model, goal test, path cost.
Got it.
The notes use the 8 queens puzzle as another example.
Yes, the 8 queens puzzle. Classic AI problem. The goal is to place 8 queens on an 8x8 chessboard so that none of them can attack each other. No 2 queens in the same row, column, or diagonal.
Sounds hard.
It is. And think about just trying random placements. The number of ways to place 8 queens on 64 squares is, well, the notes say it's huge, something like 1.8 times 10 to the 14 sequences if you place them one by one.
Wow. Okay, yeah, we definitely need a smarter way than guessing. How do we formulate that problem?
Okay, state could be any arrangement of 0 to 8 queens on the board. The initial state is just an empty board.
Makes sense.
Actions are, add a queen to any empty square. The transition model is simple. The result is the board with the new queen added. And the goal test is, are there exactly 8 queens on the board, and is no queen attacking any other queen?
Okay, I see how that fits the framework. Now, abstraction. The notes mention this is important.
Hugely important. The real world is incredibly messy and detailed. Abstraction is about simplifying the problem by ignoring irrelevant details.
Like?
Well, think about driving a car. To plan a route, you don't need to know the physics of internal combustion or the exact tire pressure, right?
No, definitely not.
You abstract all that away. You focus on where am I, where do I want to go, what roads are available, turn left, go straight, accelerate, brake. You keep the essential stuff for solving the navigation problem. Our vacuum world is also a massive abstraction of cleaning a real house.
So it's about stripping away the noise and focusing on what matters for the task?
Exactly. It makes the problem manageable. Which leads to the difference between the state space and the search space. They sound similar.
They do sound related, yeah.
The state space, remember, is all the possible configurations of the actual problem. All the ways the queens can be on the board, all the spots in the maze. The search space is more abstract. It's how we represent the process of searching for a solution. Often we visualize it as a search tree.
A tree. Like branches.
Yeah. Think of the initial state as the root of the tree. Each action you can take from that state creates a branch leading to a new node, which represents the resulting state.
Ah, okay. So each path down the tree is a potential sequence of actions.
Exactly. And each node in the search tree isn't just the state. It usually stores more info, like which state it is, which node parent it came from, the action that led there, the total path cost to reach it, and how deep it is in the tree.
So finding a solution means finding a path from the root to a goal node in this tree.
That's the essence of it. And exploring this tree involves expanding a node. That just means generating all its children, finding all the states you can reach by taking one action from the current state.
The notes then spend a bit of time on trees themselves as data structures. Why is that relevant here?
Because these search algorithms fundamentally operate on tree-like structures. Understanding basic tree concepts from computer science is key. A tree has nodes connected by edges, a strict hierarchy parent-child relationship.
Right.
There's one unique root node. Every other node has exactly one parent. Nodes can have 0 or more children. And crucially, there are no cycles. You can't loop back around to a node you've already visited on the same path down from the root. Knowing terms like depth, height, leads, siblings helps understand how the algorithms navigate.
Okay, so the search explores this tree structure. How does it keep track of everything?
Good question. We usually think of the search space as divided into 3 parts. There's the explored set nodes we've already expanded. There's the frontier nodes we've seen and added to a list to explore but haven't expanded yet, sometimes called the open list.
Okay. Explored, frontier.
And then there's the unexplored region, everything else we haven't even generated yet. The search process is essentially about picking a node from the frontier, moving it to the explored set, and adding its children, if they haven't been seen before, to the frontier.
And how it picks the next node from the frontier.
Yeah.
That's the strategy.
That's the search strategy, exactly. And the simplest types are uninformed search strategies.
Uninformed, meaning they don't know much.
Pretty much. They're also called blind search. They only use the information given in the problem definition itself, initial state, actions, goal test. They don't have any extra clues about which states might be closer to the goal.
Okay, what are the main uninformed strategies?
The common ones we look at first are breadth-first search, BFS, depth-first search, DFS, depth-limited search, DLS, iterative deepening search, IDS, and uniform cost search, UCS.
Let's start with BFS. Breadth first. What's the idea?
BFS explores level by level. It starts at the root node, initial state. Then it expands all nodes at depth 1, then all nodes at depth 2, and so on. It explores uniformly outwards from the start.
Like ripples in a pond.
That's a good way to think about it. To manage the frontier of the nodes waiting to be explored, it uses a FIFO queue. First in, first out.
Okay, FIFO queue. How does BFS stack up? Is it good? Bad?
We evaluate strategies on a few things. Is it complete? Will it always find a solution if one exists? Is it optimal? Will it find the best, least cost solution?
Right.
What's its time complexity? How long does it take? And its space complexity. How much memory does it need?
Right. So for BFS?
DFS is complete, yes, as long as the branching factor B, the max number of children a node has, is finite. Its time complexity is roughly O of B, where D is the depth of the shallowest goal node.
OB to the D. That sounds like it could get big fast.
It does. And that's also its space complexity, OBD. Because to explore level D, it has to keep all the nodes at level D in the frontier queue, and potentially all the nodes at level D1 in memory too.
So it needs a lot of memory.
A lot. If the branching factor is, say, 10, and the solution is at depth 15, we're talking about a massive number of nodes to store. That's the big drawback of BFS. But it is optimal if the cost of each step is the same, like just counting moves. It will find the shallowest goal.
Okay, complete and optimal for unit costs, but potentially very hungry for time and especially memory. What about the next one, DFS, depth first search?
DFS is the opposite approach. Instead of going wide, it goes deep. It picks one path and follows it as far down as possible. If it hits a dead end, or the maximum depth, it backtracks to the last choice point and tries a different path.
Goes deep first.
Okay.
How does it manage the frontier?
It uses a LIFO stack. Last in, first out. When it expands a node, it puts its children on top of the stack, so the next node it explores is one of the children it just generated.
LIFO stack. And its evaluation. Complete. Optimal.
DFS has issues with completeness. If the search space is infinite, it might go down an infinitely long path and never find a solution elsewhere. It is complete for finite spaces, though. Time complexity can be bad, where m is the maximum depth of the tree, which could be much larger than the solution depth d.
Goes to the M, potentially worse than BFS time-wise.
Potentially, yes.
Yeah.
But the huge advantage of DFS is its space complexity. It only needs to store the nodes on the current path it's exploring, plus the siblings at each node on that path. So its space complexity is only OBM, linear space.
OB times M. That's way better than OB to the D.
Dramatically better, especially for deep searches. The notes probably have an example showing BFS needing like exabytes of memory while DFS needs kilobytes for the same deep problem. But the downside is DSS is not optimal. It just finds the first solution it stumbles upon down some path, which might be much deeper or more costly than the best solution.
So DFS, great on memory, not guaranteed to find a solution in infinite spaces, and not optimal. Big trade-offs there.
Definitely. You trade off completeness and optimality for potentially huge memory savings.
Okay, lastly, the notes mention depth-limited search, DLS, and iterative deepening search, IDS. What are they quickly?
DLS is just DFS with a depth limit. You tell it, don't go deeper than level. This solves the infinite path problem, but now that the shallowest solution is deeper than your limit, you won't find it. So it's incomplete if you DLR.
So you have to guess the right limit.
Kind of. Which leads to IDS, iterative deepening search. This is clever. It runs DLS repeatedly with increasing depth limits. First, limit 0, then limit 1, then limit 2, and so on.
Doesn't that waste time re-exploring the upper levels?
Surprisingly, not much. Most of the nodes are the bottom level, so the repeated work in the upper levels is relatively small compared to the work done at the final depth limit. IDS ends up combining the best of both worlds. It's complete like BFS, optimal like BFS for unit costs, and has the low OBD space complexity of DFS.
Wow, okay. IDS sounds like a good compromise then.
It often is, especially when the depth of the solution isn't known and memory is a concern.
Right, that gives us a really solid overview. We've gone from defining an agent, this perceive, think, act loop,
to rationality, making the best choice with available info.
Formulating problems for search, understanding state spaces and search trees.
And then looked at these fundamental, uninformed search strategies, BFS and DFS, and how IDS tries to combine their strengths.
Definitely a strong foundation for anyone just starting with AI in their CS studies.
Absolutely. These are the building blocks you'll see used and expanded upon again and again.
So a final thought for you listening, especially the students just encountering this. Think about those trade-offs between BFS and DFS. One finds the shallowest path but needs tons of memory. The other uses little memory but might wander deep and find a non-optimal path, or none at all in some cases. Can you think of a real-world problem where you'd strongly prefer one over the other as a first attempt? What makes a problem lean towards needing any solution fast, maybe DFS-like, versus needing the best solution guaranteed, maybe BFS-like? Something to chew on.
Good question. It highlights that choosing the right approach depends heavily on the specific problem you're trying to solve.
Exactly. Well, that's all the time we have for this deep dive. Thanks for joining us.